some kind of formal, machine understandable way. This is apparently something that mathematicians are interested in, to be able to search it in some more mechanical way, but also at the same time, it's interesting for the formal proofs community that finally someone is interested in formal proofs, maybe not the proofs yet, maybe they're interested about the statements, to be sure that these are the actually correct ones. I was supposed to talk after Tom, therefore my introduction to formal abstracts is very minimal, and I actually have just like 3 lines on how do we understand what Tom was supposed to have said. The way we understand the formal abstracts is to have a system that is going to provide the statements and all the necessary definitions for the statements in some computer understandable way for all the known results in mathematics plus plus, so related fields, things from, say, physics or the examples that we discussed before that are somehow at the edge of mathematics should be included in this. The project, as I've heard during the break, is progressing well. There are now 4 people working for Tom full-time on this, so this is somehow really taking off. And right, so that's it about the project. What are the additional things that we would like about the formal abstracts? I don't think this is exactly what Tom wants, so somehow there I'm putting the barrier, but that's my reinterpretation. We want a language that is close to standard mathematics. That is, we want the notations to be extensible in the way if I want to use different notations in my theory, I want to be able to talk about it in such a way that the computer starts understanding me, and maybe even in a higher level, with higher levels of disambiguation than what is provided by current proof assistants. We want expressible foundations. We do not want the fact that all the theorems that we're specifying need to be somehow deep embedded. We want to be able to express the things that we want, and the definitions that come from mathematical text should not need to be highly reformulated so they fit in the system. A side thing that has not somehow been a major issue yet is to get a consistent library, so that it's not the case that this formalization introduces real numbers in this way, the other one in another way, and they start being incompatible. Since mathematicians agree that all the real number structures are somehow isomorphic, well, in fact, this example that I'm talking about has been proved in Coq, so maybe that's not a very, very good example, but if there are multiple ways to state things and it's not clear how to go about it, the library should be consistent and general enough for people to be able to use. Okay, so that's somehow an intuition that we want to add to the project, and the project has been recently more and more focusing on the lean proof system. Here we're not really proposing an alternative, but discussing somehow positive and negative sides of it, what could be done to somehow make it more appealing to people like John, who said, well, we want something that's more set theoretic, or others yesterday as well. So the F-Abstract project has taken inspiration from the various proof assistants, in particular the features that I like throw in as the ones that we want. So we want the best from all the systems. From Hall and Isabel Hall, we would like to have some kind of simplicity of foundations, as John showed an example from Matita, how complicated the rules can be. In fact, somehow figuring out what the intricacies of some of the rules of the code foundations are means that I have to send a PhD student for a visit to France so that they can figure this out. But well, we're getting there. There are some ways to reformulate it. So this is not the negative side about, say, time theory, but can we do something easier? Second, ease of use. A person starting to work in some kind of whole system can achieve things pretty quickly, whereas in other systems it's maybe not so much the case. And the notations, this is especially the case for usable whole, where it's very easy to add not only some mixed notations, but also your own parse translations that perform some kind of additional disambiguation based on the context of expressions, which is a pretty nice feature. On the other hand, there are lots of nice things from type theory-based systems. The foundations are powerful enough to express, well, this is not a conference about foundations, so I will abstract from saying anything that I'm not completely sure about, but reasoning in many domains. I will not say everything too. And especially that we have Frank here with his QED paper. He at some point claimed that some things are not so nice to be expressed in any of the existing systems. Last time I talked to Frank, he said that the situation hasn't changed. I don't know if it has changed since then. Okay. And then there are some set theory-based systems, but so far there has not been so much that the project has taken inspiration from. What could it be that we could put in there? Well, maybe the foundations of set theory-based systems are more familiar for mathematicians. Maybe, well, that's something that has been said already multiple times in this meeting. The soft types. Types are definitely good. We've seen examples where, thanks to the type system, some proofs go better, but on the other hand, there are many situations where you have to fight with the type system. Can we get something where we get the types, but they do not slow us down? Nice reasoning about various kinds of structures. I will not say more about this. We'll see it in more practice later on. So an example of such a set theory-based system we have this kinds of features would be Mizar, and I'll just shortly remind some of these features of Mizar that the project could take inspiration from. So the Mizar proof assistant is quite different from the other ones because it has been developed by mathematicians for themselves to do their proofs. 3 years ago at the QED plus, what was it, 20 workshop, I heard a statement from mathematicians saying, well, I don't use proof assistants because they slow me down. If I'm doing my proofs, if I'm writing them on paper, I write it faster than with a proof assistant. It takes me so much more. But there are tools that help me. A computer algebra system helps me if I need to do computation. LaTeX helps me because I'm getting something out of doing things with it, but the proof assistant does not. Can we get something like a proof assistant, but something that helps me a bit with the proofs, but it doesn't slow me down, something that would just let me do my things, and that was somehow the way Mizar has been created from the beginning, that it started as a typesetting system. It started as a LaTeX-like tool, which later on got proof checking added on top of that as an additional feature. Mizar started in 71 as a typesetting system, but the actual start of Mizar 73 is the start of Mizar as a proof assistant with a consistent library of formalized math, with natural deduction-based proofs, which are arguably much nicer to read for mathematicians than long sequences of tactics, and the foundations are based on set theory with universes used by only few formalizations still there, and it includes a soft type system with things like dependent types, so you can get some nice reasoning and a type inference mechanism. Maybe some of these features could be interesting. That's my thing. All right. So how does this? What are the other kinds of Mizar features that we could include? Mizar includes this very nice, rich input language. So for a symbol like plus, there is 140 something interpretations of the symbol. Do you mean the plus of the real numbers or of the integers, but also plus on groups, on matrices, and so on. And the same symbol is enough. The system can interpret which one is it that you mean in any context. there's also some generation of readable formalizations, and since the Nizar team has been producing LaTeX versions of the formalizations already for many years, this has been perfected pretty well. I think I have this on one of the slides later on. The focus has been on mathematics. There is quite some theories that have not been covered elsewhere, such as the part of the compendium on continuous statistics, but much less computer-related proofs than in typical other libraries. The system has evolved. It has various new features have been added with somehow the progress of time. Unfortunately, a number of features have not changed since the 80s, which was one of the main reasons why various people asked by Tom Hales if you should use Nizar for the formals abstract, said no, you shouldn't. Yes, there's lots of nice features about it, but there's also so many problems that are much worse than in the other systems that you shouldn't go there. So could we get something like Nizar, all the features of Nizar, and get them in a modern system, for example, in a logical framework? That's the question I'll be trying to answer today and show our progress in that direction. But still, just to come back to these features, we have this, how is proof generated. This is the completely computer-generated text of the formal proof of the square root of 2 being irrational. I mean, I had it at some point, but we adopt some conventions about some variables being numbers. We consider it. We say, what does it mean that something is irrational? We introduce some synonyms, and one can prove that if b is prime, then the square root of b is irrational. This is generated from a formalization, which actually the formalization itself is pretty readable itself as well, for b being element of not such that b is prime, whole square root of b is irrational, with something that follows. Well, we've already seen a little bit of this in Sean's talk this morning, how this process can be reversed. Okay, so how would you go about encoding Nizar in a logical framework? The first thing is you have to get a logic in which you're going to define the set theory, and it's enough to use something like first-order logic, because the features of Nizar that go beyond first-order logic can be encoded in the logical framework itself. So things such as set comprehensions, which do take some lambdas and so on. But of course, if you are a fan of set theory in simple type theory, there is no restriction about this. If you believe that there's a model of that, which some people claim they have as draft of, but I have not seen a real one so far. You can define the meta types, the type of sets, and the important thing is that somehow the main difference already starting at this point, how does this differ from something like Isabelle ZF, that we introduce a type, a meta type of Nizar types. The Nizar types seem to be similar to predicates, but since they are treated by the automation and in the system in many different ways, we introduce them in a completely different namespace. Nizar itself distinguishes inhabited types from non-inhabited ones, and rather than introducing separate words for these, we just add a predicate, a meta-level predicate that says a type is a Nizar type is inhabited if there exists an element in it. Examples of such Nizar types: and even natural number. So we have a predicate that some object is even, it is natural, and it is a number, and this satisfies all the requirements that have been asked for in previous talks, that, well, this natural number is also an integer, is also a rational, so it has other properties. If you want to think about it in some more type theoretic way, you can think of this as an intersection type, something that is both even and natural and a number. Or when it comes to things like dependent types, we have a bijective function of AB, so functions from A to B. So then, given the these meta-level types, we start introducing the constants. what do the constants need to do? They need to be able to construct Mizar types, actual meta-level functions, where the functions can also be constants, such as the empty set. We need to be able to define the empty set to somehow bootstrap our set theory, as well as user-level typing rules. So there is some typing mechanism, but since we are introducing user-level predicates for these, we need to be able to say something about the actual rules. So we're introducing a type membership operator that says an X is an element of a type, and we have operators for defining a type and the standard choice operator. So what axioms do we have to specify these constants? The first thing is the axiom of choice. To follow Mizar, I'm here abstracting of whether it's the right thing to do. What does it mean to define a type? The intuition is that we are defining a type which is that is a subtype of another type. So we have a parent type together with some condition for conditional types and the actual property that is being defined. We want to also talk about non-objects, or something like a non-negative, non-event. Right, so a non-negative number would be something which is in a type that is a non-type. So we are able to, using the previously specified constant, define it. This is some object such that the negation holds about x being of the type A. From this, we can derive the property x is non-A if and only if not x is A. And then we get these intersection types that say x is of the intersection type T1, T2 if it is in both of them at the same time. All right, so with this we can start to define the notations. The Mizar-style notations in our framework are not as close to Mizar as we want them to be, but we can write things such as X is a set, it's an empty set, it's a non-empty subset of natural numbers, and so on. And also notations for formulas. There are limitations to what Isabel can do, and that's similar to what other systems say Overly can do, but Mizar is stronger in some ways. I will not go into details here. After specifying the methodology of Mizar, we have to somehow start with set theory, and set theory assumes some notions, some basic notions, such as being a set, being a member of a set, and this is already a part of Mizar that is expressible in the language, but is not a part of the axiomatization of set theory. That's why it's called somehow the hidden article, which specifies the type of sets, equality on sets, and set membership. Using these would be the last axioms that specify the system. Using this, you can already start specifying the standard axiomatization of set theory. And we are pretty close to that of Mizar. On the left side, you see the Mizar one. On the right side, you see what you can write in the Isabel Mizar object logic. I'll just read the beginning. For x holds, x is a set. And then we have theorems of extensionality, axioms of pairs, axioms of unions. They are as expected. For xy, there exists a z such that for a holds, a is in the z if it's in the first one or in the other. That's the standard formulation of the axiom of pair. Here we're doing this, well, maybe with a little bit different default notations, but both of them can be input and they're meaning the same thing. There are some things that have been axiomatized in Mizar, but we are able to prove them using previously defined things. I'll also not go into it in this talk. Given a basic specification of the theory, you can go about supporting Mizar-style definitions. Mizar has a pretty well-developed package for definitions. It supports things such as conditional definitions, so you constantly define only under a condition. You can specify things by means, so a property of an object rather than just by equation. So you can think of this as definition by a choice operator, but there are some things that you have to fulfill. If you're defining a type by a choice operator, it starts to get a bit more complicated. So type definitions, definitions of structures, and a slide on structures as well. So we've created a simple definition package in Isabel that lets you create this kind of core definition just by equality, and given the necessary user obligations, derives the derived properties that are equivalent to those in Nizar, but they're immediately usable in the frame. So now we can define concepts such as a singleton set. So define, given a y being an object, a function, singleton y returns a set is such an it that x is in that it, so it's in the singleton set if it is equal to the y, precisely what we would expect, and also quite similar to the Nizar notations. Just to Nizar, just we have to explicitly specify the notations for each of the concepts. Otherwise, we're getting some default ones. Okay. Let's go to structures. If we think, so that was also something that was mentioned yesterday. If we think about specifying mathematics, very many domains talk about structures. Let's consider a ring. We have a carrier, a plus, 0, times, and a 1. How could this be modeled? In Nizar, there is a syntax for doing that, there's a syntax for doing that, but the specification is somewhat unclear, so we have to model it somehow. We have a carrier that is a set, and the add, so the addition operation is a binary operation on the carrier. The 0 is an element of the carrier, and so on. We're going to model structures using partial functions, and that's a pretty natural thing. Where do we get the partial functions? Well, if we process the first few articles of the Nizar library, then they start defining these pairs, then ordered pairs, then relations, and then at some point you get partial functions. And the first use of structures is after that, so we can actually define structures using the set theoretic partial functions. And we're getting a pretty similar syntax, just that these operations has to refer to the object itself. So what is, let's say, a 0? A 0 is the element of the carrier of the structure itself. In Nizar, the syntax does let you skip these arguments. It's an element of the carrier, but actually, if you want to be fully precise, this is a lambda expression that refers to that original S. So now we are modeling the structures, but so far what we said is we have a structure that contains a carrier and some values and some operations. Is this a ring? No, it's not a ring. And the cool thing that we have in Nizar is we have this type system that lets us use intersection types. So we can say a ring is this kind of structure that is abelian at associative right 0 and so on. But this immediately means that something like a relation about a field and a ring is completely obvious. One is immediately an instance of the other because it just has a bit more types intersected with the other. And that's the cool thing that these start being associated. That's the thing that we wanted, not only for natural numbers being always being real numbers, but we also wanted for some of the algebraic structures and more complex examples. I hope I'll have the time to show you one example. Okay, so let's head on to an example of Nizar proof. A Nizar proof about something about group theory. Let's reserve G for a group defined in the way before. Reserve G and H for elements of G, and then we're specifying that the inverse of the operation applied to H and G is again the product of the inverses in the opposite order, and the proof follows by some equations. Can we imitate this kind of proofs? Well, my co-author has spent a month of his life fighting with big parts to optimize this to make sure that we can do as close as possible. So we have somewhat more syntax clutter, but it's quite close. We reserve the G and the HG for elements of the structure G, and now the theorem has to explicitly refer to the operations. So the product is the product in the group G, and the inverse is also the inverse in G. That's something that we you complained about yesterday, can it infer it? And so far our syntax cannot do it, the one of Nizar can. But with some syntax translation, you can try to get that in most cases from the context which of the groups you're talking about, because you usually have only one group. If you have multiple, then you can always specify that that's the situation in Nizar, and the proofs because of this become longer, and we are trying to imitate the Nizar by an Isabel tactic, which works in, well, 50% of the cases, 50% of the cases, you still have to add some additional information at the moment. So that was the Nizar includes type inference, and for this kind of types that the user specifies, you specify what does it mean that the number is an even number, and then you have the number plus 1, and apparently Nizar can infer that that is an odd number because you specify the type inference rules about that relate this kind of concepts. So there is a syntax called clusters, which means user-defined type inference rules. These are theorems that you have to prove, but after you prove such a theorem, then you know that every y-valued function that is a y onto and 1 to 1 is a y-bijective function, or another rule that says if f and g are functions, that g composed with f is a function like, we don't say that it's function because we still have to map some things, but we get some properties. Can we do this? Yes. We also implemented type inference in Isabel, and it derives all the properties of the proof. And in the particular proof from before, at the maximum point, like here, before the auto, it has derived 35 judgments about the objects in the context. These are automatically derived and available to the proof procedure. Information such as that the group G is unital, that something is an element of the group, or the carrier is non-empty, just based on the things that are available in the context. Some other examples of statements in Isabel Nizar. What are the natural numbers? Well, the natural numbers, if you think about it mathematically, are the elements of omega, the subset there, and that's how it's defined in Nizar. And you define the induction on natural numbers. So you prove the induction on natural numbers. How do you prove the induction on natural numbers? It's a special case of the induction on ordinals, and this is the actual statement. If A is a natural number and P is an empty set, then we show that for every natural number from P we derive the P of the successor of N, and the successor is the ordinal successor, the standard thing that takes the element and it in itself. It shows that property, and that's a very quick proof because it follows the induction for ordinals, which is also proof, but that takes more time. Another example is something from computer science. There's still computer science, so this is a proof from Turing machines, which says that the half instruction of some simple Turing machine is halting in that machine. Not very sophisticated fact, but well, that's one that we ported manually. Okay, so we've been porting, or actually Karel was doing the porting. Well, I was developing some of the infrastructure of about 30 Nizar articles. So we have almost 1,000 different kinds of theorems manually written. Can we do this automatically? And we started the semi-automated translation where the export from Nizar is defined that combines the syntax, the actual things that the user typed, with the semantics, how it was processed, and Isabel can already import, but it's a very big import, the first 100 MML articles, and I'm saying article here, as in the abstracts of the articles. That means all the definitions, theorems, and user typing proofs are imported and become usable. The proofs are exported, but so far I have not got there yet to process them. Right. But what it gives you is it gives you a usable environment to develop things further based on the Nizar library, but using a modern interface. and it's all fully specified in a logical framework. You have well-defined procedures, and Carlo has also proved some properties of factorial and exponentiation just based on the imported part of the library, so the imported natural numbers based on the imported ordinals and other. And these natural numbers are those that have been cut out from the reals and so on, like we wanted them to be. Okay, so I've tried to tell you something about some features of Nizar that could be useful for F-abstracts. And the features would be more familiar mathematical foundations. I've already heard that for a few of you it may be appealing, but not for everyone. Convenient proof style, actual support for mathematicians. The mathematicians develop Nizar in such a way that it helps them doing their proofs. So the hope is they like it. I don't know. And another thing, the Nizar library has a committee that has been taking care about the quality of the submissions, making sure that it's all integrated, well, in the sense that there's only one definition of every concept, and if it's not the case, then they ask the person submitting to synchronize them and so on. This seems to have worked pretty well up to a certain point when it's getting big, but we do have a library at the moment, the biggest library of consistent notations. The AFP is trying to do a similar thing, and the countries are trying to do a similar thing, but, well, there is so many incompatibilities, you cannot load some of them together, the definitions are different, so that's something that would be, in my opinion, a very important thing for F-abstracts. Can we somehow specify a process that is going to let us have a large consistent library? And I am the one pushing this more because I'm a person doing some machine learning for theorem proving, and for that we do want to have a consistent base of things so we can learn on it better. And then hopefully when we learn on it better, we can abstract more, but that's not the first step. Thank you.
Thanks to the speaker being extremely disciplined. We have plenty of time for questions. Starting from the Dutch person over there.
So my main right is these are and stop using the system is that it doesn't allow 20 types. You said something about it, but I missed what it was. Do you support 20 types?
Yes. So these are types. So there are two kinds of types in Nizar. The Nizar literature refers to them as modes, which have to be non-empty, and well, adjectives, attributes, and there are some combinations of those. I will abstract from the keywords that they use. We have one concept for types, and then an additional property that you prove about it, which is that the type is inhabitant. The inhabitant is a property that will be something that will be needed for some operators, such as the choice operator, in order to apply choice. So choice is specified in such a way that it only gives you the appropriate thing if the type that you apply to it is an inhabitant. And we have an infrastructure that gathers such inhabitation information and derives it in a similar way to type inference. It's a bit less developed than type inference, but yeah. So yes, you can specify the type that for which you didn't prove that it's non-empty, but at a certain point, if you want to use it in a particular way, you may have to be need many really necessary.
These are every time you use the type and prove, you need to prove the choice, right?
There are many situations when you have to do it, and we have specified it in such a way that it's only there when you actually do it.
So that's more less mistaken.
We try to make it as consistent with Nizar as possible, but also avoiding the restrictions that have been introduced that are unnecessary. So we believe that the system is consistent, but yeah.
I guess time for one more short question. The other Dutch member of the audience.
You used the word consistent.
Okay.
I was thinking of something else. In your case, consistent means that the notions fit. I was thinking of logical consistency. Do you worry also about that?
Okay.
Can you introduce action? Do you introduce axiomatic statements in the abstracts or not?
All right. So I have shown you all the axioms that have been specified. And the axioms are essentially a specification of the foundations of Miser. So we have a possibility to define types based on predicates and to apply them. We have the axiom of choice. We have the standard set theory axiomatization. Okay, it's maybe not standard because it includes universes, but it's the Tarski-Grothendieck axiomatization of set theory. These are all the axioms that have been introduced. Everything else is proved based on these axioms. When it comes to consistency, well, we do have, I mean, what does it mean to have a model of set theory in set theory? I mean, if we trust set theory, then it's just...
So if in an abstract some axioms are assumed, then it's the responsibility of the user.
Right.
Right. No, that's...
It's not, I think it's
All right, so I said that this is based on Isabelle Fall, but you can also load it to Isabelle Fall, and then you get Sledgehammer and Nitpick. Then the foundations are a bit less safe, because we're adding lots of set theory and other properties on top of Hall. But you can use Sledgehammer, you get some proofs, and then you've got some information, you can rewrite it so that it's again usable with Hall, and that's a practical way of developing proofs.
Have you tried to get a model here?
We have not worked on this. Chad Brown has somewhere a hint about how to approach building a model. I have not developed this in detail. I must be really more opinion. So this was for his EGAL project. He has in the manual something about the model of set theory in simple type theory, which is as close to Isabelle as.
Thank you very much.
So again, like the schedule has been shifted thanks to the main person not being here. So this is.
You're not here either.
Second.
Apparently, you're not here either.
Close. There are some buts in these slides. You can count them. So this is basically. This is yesterday's slide anyway. Oops. Yes, progress. I'm the busy chairman. To give you an idea, the proceedings which you can download from the web page, I did on the train to Oslo over to Moyan. So, well, excuse my imperfect slides. So anyway, this is like a progress report on what we have been doing in this money auto-formalization project, in which Cezary is obviously also involved a lot. And I should say that Chad Brown sends greetings to everybody, and he really wanted to be here, but because he has all these traveling restrictions, he decided not to. But if we organize it somewhere closer to Prague, he will come again next year. And he really was very interested in this whole topic of formal abstracts and maybe using some more theoretical functions for selling formal mathematics to mathematicians. And actually, as we talk, he's working on his own theoretical framework for formal abstracts. And by the way, he has already imported like most of Cezary into his own high-order logic on top of set theory framework. So if he was here, he would give a very interesting talk, but he's around. So this is about about this general project that we started about 5 years ago with Cezary and other people. When we said that maybe time has come when we could start to attack one of these 2 points. Like so far, like most of our work has been on this using machine learning and AI for theorem proving. but maybe let's start to look at also the other point, which is preventing like strong computer support for mathematicians and that this sort of painfulness of formalization. And like given that like this was before like AlphaGo or something like that, but like we could see that machine learning is being used already in theoretical. So why not? There was this Google Translate which like was improving and improving, right? So why not try some of these crazy ideas again after some time? So one important point in this project is that we saw this proof-wiki corpus, and in 2014 we did a very basic experiment on the proof-wiki corpus, which is basically informal mathematics done by mathematical enthusiasts with the sort of intention to have the proofs really well explained. So the guy who is behind proof-wiki basically accepts submissions from everybody, but what he does consistently is to rewrite the proof into his house proof style. Then every call it proof command, proof step is on one line, and his proof style is very limited. And I would say he has reinvented the Jaškovský-Fitch proof style. Basically, he has let assume suppose then and so this was we saw it actually in IMAX in 2011. We organized this Maths Wiki workshop and invited him, and it was like a big surprise for all of us who were there that these people have independently come up with something which really resembles the sort of design proof style. And this was one case where we said like this would be an obvious candidate for trying some machine learning, some Google Translate between informal and formal, between the proof-wiki informal but very formal thing and the design thing. So what happened is that Gregor Cezary, who unfortunately passed away so long ago, started to work on aligning Cezary with proof-wiki, and like by the time he died, like he managed to create about 500 alignments between proof-wiki. So there are like over 500 proof-wiki pages, which is a pretty substantial part of proof-wiki, which are sort of directly mapped to their Cezary counterpart, and we can do all sorts of crazy machine learning stuff on that. So just to remind you how old we are, this is the crazy claim which I sort of 4 years ago at this Paris meeting declared. So you can probably still have me. So in 25 years, 50% of top-level statements in late written master-level math curriculum textbooks will be parsed automatically and with correct formal semantics. And the only person who has bet me so far is Craig. So if
what direction did he get?
oh, he's a pessimist. You should know him.
Yeah.
So this is a bit about the landscape. So we have these formal corporations, these like tens of thousands of theorems in them. And we also have these informal corpora which are much bigger. So archive is probably over 1 million articles now. Wikipedia is getting pretty big, and that is this proof-wiki. So somehow we want to use the knowledge, the energy which mathematicians put into the informal corpora, somehow at least start to transfer it to the formal setting. And this is the sort of approach or plan that we have followed so far. So because we don't have so much data to throw it to some neural network we basically started by creating the data by faking the, the informal correspondence of the formal texts that we have. So we sort of apply some ambiguation procedures like you have seen in Sean's talk, basically the Jaguars translated examples like that, which is much more ambiguous. Because this is still not too much data. We have started with non-black box architectures with some neural networks like probabilistic grammars. And the good thing about this non-black box approaches is that we have implemented it all and we can modify it at various places by, for example, some semantic pruning directly by typing, for example, into the parsing framework. And like the sort of rapid development idea is to quickly get it all the way from the informal to the language of the, let's say, formal proof assistant to some sort of ATV translation done by some hammer tool, and basically have this whole feedback loop between the sort of statistical parsing of the informal stuff to the feedback which the automated theoretical gives you and do some sort of reinforcement learning from that. So this whole idea we have actually sort of succeeded with creating this full big thing. And then the plan is that we gradually employ more sophisticated machine learning methods and test it on more complicated informal corpora or phenomena. And like maybe we will not need precise alignments of formulas, but we will gradually be able to infer a lot just by aligning chapters or sections. And like when Tom Hales in his FlySpec book says, like, this is the top level lemma, and then some FlySpec person in analysis spends 1 month developing one full file of FlySpec. Then even the high level alignment of the top level lemma will sort of propagate into the alignments between the sort of smaller steps. So that's sort of one plan how to sort of extract it. And like I think the thing which, for example, the Google people I hope started to work on and might tell us something about is that there's also information, a lot of possible learning just on informal corpora. For example, you can learn various synonyms or various versions of mathematical formulations. And when you have just one version of that synonym in the formal language, the learning on the informal part will give you a lot of options how to are the informal statements and map them into the one sort of formal thing. So that's another way. And obviously, like what Sean was showing here, like it's sort of end-to-end. Let's use deep neural methods. That's also like an alternative. So I should say, like you might say that this is sort of attacking it on several fronts, but this is what automated theoretically people typically come up with several complementary strategies because there is no silver bullet. So I think Tom Hales once said that Grothendieck was defining this rising water strategy for solving problems. So instead of just solving the problem directly, which is very often impossible, you sort of start some push to develop various methods in that direction, and eventually something will work. So that's the general plan. So briefly, what we did before, like you have seen it in the previous two AITs. So we took FlySpec, polite, informalized it by ambiguating what is non-ambiguous. That gives us an aligned corpus on that we train basically a probabilistic parser. And then we sort of evaluate the probabilistic parser complemented by type checking both inside the parser and after the parser. And then we use like fully hammered sort of prep selection and ATP to improve the results. And that's been working better and better. There's all sorts of improvements. So we have something like 80% success rate when we count the top 20 parsers, like whether the correct parse is among the top 20 parsers proposed by the statistical parser, and like something like 60% when we are only looking at the first parse, basically. So that's thanks to a whole being a very simple language. This is how parse is so if you're interested. So like because we are too successful, we need to do something more complicated. So Cezary is much more horrible. And, like it's being designed by this guy who was a linguist among being other things. So there is much more overloading in Cezary and things like dependent types, hidden arguments, synonyms. And what I talked about last year is that some of these things are so horrible that our sort of limited statistical parsing framework cannot do it at once. Like you really need some sort of neural networks to complicate transformations. So we decided to do it in 2 layers. One layer is what the Cezary people call a pattern layer, which basically resolves the overloading. So that when you see plus, it tells you sort of which plus it is, but it doesn't tell you, for example, it doesn't fill in the hidden arguments, which is a pretty complicated procedure for which you need to know the types of all sorts of other things in the context. And then the second layer is the sort of semantic, the Cezary terminology constructor layer, where, for example, all these hidden arguments are completely elaborated. The types are resolved, and we can run the automated through. So that's what we did. This is the example I was showing last year to sort of show people how crazy Cezary is. You define composition of relations using this hash in brackets. Then you define a synonym for it, this star symbol, so it's the composition of relations. And then you overload this notation for functions by changing the order of the arguments, because somehow the mathematicians think that functions should be composed in a different order than relations. So good luck with parsing this. So our ATP, so last year we had this ambitious idea that we will just take all the sort of Cezary typing rules and the sort of prolog style rules which encode the relation between these user level, this pattern level syntax, and the semantic level encoding. And we will just give it to automated frameworks and they will do the magic for us and figure it out. And it didn't work. Oh, I mean, it worked a bit. So we got something, eventually we got to something like 60%, and it was in 60 seconds, so that's quite a bit. And eventually I found that the encoding is unsound and the unsoundness doesn't show too often, but it looked like an issue. And it was slow, and we could probably make it sound, but then the ATP encoding would be even heavier, and we wouldn't be getting much from that. So that's like for an AI person, this is like a declaration of a failure, right? Like I expected the AI to do the work for me, but it's not strong enough. So now we have to work. So what basically Chat did, I took him several months of work, is that he really implemented basically Nizar style typing and elaboration inside the probabilistic chat parser. And it's a sort of a non-trivial algorithm, so it's very saying of itself because it's probably like when we along with Cezary and Karol have been doing one of the only public approximations or redoings of racial reconstructions of what the Nizar people are doing in this material elaboration and typing sort of recursion. And so there are some issues, like in Nizar, typically works when you sort of bottom up, when you know all the types of things in the context. And when you are parsing in a chart parser, you are parsing incomplete formulas, you are sort of parsing chunks of stuff. So one thing with chat has to do is to basically sometimes assume some typings of some free variables when it's parsing.
Is the chart parser like a CYK parser?
Yeah. But like now we have it, and it sort of seems to work. So when we test it on the sort of top level Nizar formulas, we can basically elaborate about 95% of them without any additional assumptions. And it's sort of more tricky if you are in this sort of partial world and you are only parsing chunks of the formulas. And we haven't done the ATP evaluation. This is sort of the pure statistical parsing evaluation on Nizar. So this is before this is before we included the chats extensions. Chats extensions don't really improve the 64%, and again, top 20 parsers too much, but they very significantly improve or sort of decrease the 2.61 number in the average rank of the correct parse, because he picks out many of the non-type parses. So I think it goes built with all these extensions. Now to Proofiki. So this is the motivational example which we sort of together with Cezary for Kickham 14 to impress people how easy it is to translate Proofiki to Nizar. So on the left you have something which is written in Proofiki, and on the right you have two Nizar proofs. The first one is what is really in the Nizar library, and the bottom one is the one with sort of hammering. So the ATP in the brackets says that the user just called the sort of Nizar hammer to discharge this proof obligation. And so one of the points is that the proof on the left is sort of buggy. So if you stare at it for long enough, you will probably find about the typos, I think. The other point is that the proof on the right hand side is sort of pretty much a reformulation of the proof on the left hand side in the Nizar proof style. So if we train something like Sean was showing to take the sort of layback or proof to the Nizar syntax, then hammering might be good enough to do the full proof in this smallish case. Yes. Can we do this? Can we align Proofiki with Nizar and pass it and do theorem proving from that? So as I said, Tegros started to do this, and it's not like what he did for Sean, that he just said that I can ultimate program which would generate a webpack. because the people wouldn't take it. So you have to adjust to what already is in Logical, what sort of concepts are defined there, how they formulate things, etc. So it's been quite a lot of manual work, and because of that, it's probably a more valuable data set, like than the automated translation, because there's much more manual work and it's much more heterogeneous than just some homogeneous translation to later. This is probably the simplest example which Chet and Pierka took and started to think how to align it also between the two corpora. So on the top you have the proofreading code as it is there. The second line is how it sort of displays in Wikipedia, the computer engine that I'm using for rendering. Then you have the Cezary statement, sort of corresponding to this in some way. So you can see that, for example, in Cezary chain is written with capital C, whereas in Wikipedia it's lowercase c. And then you have the Cezary ASCII, which is basically the representation that is used for creating the programs. So now our very easy and simple task is to take the thing at the top and produce the thing at the bottom. So here's a couple of issues. So for example, this chain seems to be a pretty easy thing because we have the sort of user notation tag for this Cezary chain, which is this MM2 orders 2, which is sort of serial number of these Cezary notations. And we can just say that we apply this tag also to capital chain, for example. So this is really easy to accommodate modulo and doing some sort of mapping of synonyms, like some sort of statistical mining of synonyms, which tells you that this 99 probability lowercase chain is the same thing as capital case chain, etc. The next thing is sort of tougher. So you have this piece of latex, this left x right, bracket x right bracket, whatever, and that well sort of needs to be mapped to some Cezary style parsing subtree, and like the statistical parser that we are using is too weak for this. So this is outside the framework we are using. Like the framework which Takuya was presenting might sort of handle that. Then there are all these like expansions, like ordered set translates to non-empty, like this relational structure, and something that is actually true. And then you have these like bigger correspondences between phrases, like put and nothing to follow, so as I said, the first one is quite easy. The general thing which Jirka came up with is basically to enhance the parsing framework, which is sort of a simple statistical framework, with arbitrary-list programs. So basically, what we now allow is that at sort of any non-terminal position in the sort of ASCII, we can insert a call to a list function, which will do some reordering or some arbitrary transformation. So this is extremely general, and obviously we will ask how are we going to produce these non-trivial transformations. And the honest answer is that like we haven't done it yet, and we don't have much experience from doing that. So again, like the general idea would be that we would somehow learn it, some sort of feedback loop, where we have sort of smuggled into the parser some code which tells us like what are the failing places, and then we sort of have the proof into Mizar purpose, which we are repeatedly going through, and it's giving us a database of these sort of failed fragments. And on these sort of failed fragments, we basically try to learn very simple list functions, possibly adding some sort of manually coded list functions, which are doing some of these transformations. And like there are sort of simple machine learning methods like different programming or genetic programming, which might do some of this building of appropriate functions which do these transformations for us. But like this is sort of at this point this is a project proposal and not something for which we have data. And obviously, like at some point, again, the times we use the whole feedback loop to share figures, so make it better. Oh yeah, that's it. Okay.
I have a few questions, not too many, so if you carry out the overview, we can have this in the break. Okay, Hank.
It's you or somebody who looked at Bourbaki text because you wanted well-written proofs, and Bourbaki seems a good candidate.
So we need not just that, but somebody like Grzegorz who would align it with some formal text.
Okay.
Like there are different parts of the project where, like for example, I think what Christian or Sarah will present is that they are trying to align different informal corpora, and for that, Bourbaki would be a very interesting purpose to have. So if you have some LaTeX sources, for example, it must be part of LaTeX. But in general, I think Christian will advertise, we are definitely after as much LaTeX expressed informal mathematics currently as possible, and we even wrote to Govers to give us some big Princeton companion, whatever, because we would really like to do this sort of informal mining for synonyms and alignments, etc.
So we have 5 minutes for a break, and then we move on to the second half of the formal abstracts. So thank you.
I would recommend how
No, we have to do it. Yes, exactly.